put in brackets here, I'm just going to put almost inverses. Okay? They're almost inverses. And the reason that they're almost inverses is this damn annoying constant. So we can talk a little bit more about that. Maybe let's prove it first. But again, if you actually can I do it now? Let's see. Do I need anything that from after the proof? No, I guess we could probably do it now. Okay. So they're morally inverses, and let's think about it. So if I took the integral from a to b of f prime of x dx, right? Then according to FTC2, if I wanted to evaluate this, I need to find an antiderivative of f prime. Well, there's an obvious antiderivative. What's an obvious antiderivative of f prime?
F.
F. Right? Or actually, why don't I do, let's make that a to x. And then let me change the x's here to t's. Just the t, and then we get f of x. Right? Okay, great. So it looks like if you think of f prime of t being, again, there's a derivative operator here. When I took the integral of the derivative, I almost got back my original function, right? Not quite. I didn't get back f, which is what I would have wanted, right? I got back f of x up to a constant, right? So they almost canceled each other out, except for that constant. It's even better if you do it in the other direction. So if you take the derivative, right? Well, according to FTC1, this is a bona fide antiderivative, right? And you get f of x. There they actually do cancel each other out perfectly. And here they almost cancel each other out perfectly, right? So integration is a right inverse for differentiation, and differentiation is the left inverse for integration. However, integration is not a left inverse for differentiation. Okay, it's close, but it's not quite. And again, if you're willing to think, you remember at the beginning of the year we talked about, like, you know, if you're left invertible, then you're injective, and if you're right invertible, then you're surjective. These are, if you take your set to be the collection of, for example, functions, and you look at integration and differentiation, one of the things that you get is, well, integration is certainly surjective, right? Because integration is left invertible. Therefore, differentiation is, oh no, sorry, integration is, what did I say? It's left invertible, yeah, and it must be injective. Differentiation there would be surjective, therefore, because you just put any function here, right? Any function there would work, as long as it's integrable. But they're not bijections because they don't actually invert each other perfectly. And so there's a cool thing that you can do here. I don't know if you'll do it in 240, but again, you can look at the vector space of like continuous functions. And these maps are linear operators on that space. And you can see that, like, when you do this composition, they don't perfectly cancel each other out, even at the linear algebra level. So that's a cool thing that you can see, especially if you work on like the finite dimensional vector space polynomials or something like that. Okay? So anyway, morally they're inverses. All right, now it is time to do some proving. And again, I think that, like, despite the fact that it's called the fundamental theorem of calculus, it is profound. It is, you know, it's a big deal of a theorem. It is surprisingly easy to prove. Like, it doesn't require any complicated machinery. FTC2 requires a little trick, but it's a really slick trick. I think you'll like it. All right, proof. So, let's do the following. So first thing we want to do is we want to show, so FTC1 says three things. It says that capital F is continuous. It says that it is differentiable wherever little f is continuous, and that it is an antiderivative of little f. So the first thing we should do, we should prove that big F is continuous. All right, so let's show that F is continuous. Okay. And what we're actually going to do is we're actually going to show capital F is uniformly continuous, right? Which will imply continuous. So in order to do this, let's realize the following fact. So let's say note that if x and y are just 2 points in AB, then the integral from a to x is equal to the integral from a to y plus the integral from y to x, right? And so the integral from y to xf is going to be the integral from a to x minus the integral from a to y, that's f of x minus f of y, right? And already we're kind of seeing FTC2 show up, right? Because, yeah, we're trying to claim that this is an antiderivative. We haven't proven that yet. But somehow, if we believe that it is an antiderivative, we're saying, look, I can evaluate the integral of f from y to x just by, again, plugging these endpoints in, right? So again, we're sort of seeing FTC2 pop out here. Okay, so now, remember that because we assumed at the beginning of the theorem, I've erased it since, but we assumed at the beginning of the theorem that f is integrable. And integrable functions are necessarily bounded, right? So what I'm going to do next is I'm going to take the supremum of f over all of AB. Let's name that something. So set m to be the sup x in AB of f of x. Let's do absolute value. Okay? So that, maybe let me use the different board. Okay, so we're going to get the integral of f of x minus f of y is going to be equal to the integral from y to x of f. Right? Haven't done anything there. That's just this equation. I've put absolute values on everything. And then we use subnormality of the integral. Right? That's one of the properties of the integral we talked about. Now, the absolute value of f of x is always going to be less than or equal to m, right? This is a constant, right? So if I pull that constant out, I'm just computing the area of this rectangle whose height is 1, or if you want, this rectangle whose height is m and whose width is x to y, right? So this is going to be like that. And if you look at this, this means your function is uniformly continuous, right? You see that? Because if I were to let epsilon greater than 0 be given, I can choose delta to be epsilon over m, right? And that doesn't depend on x or y. Does everyone agree? Do I need to actually write that out? Everyone's okay? Okay, so f is uniformly continuous. Didn't I give this to you as a test question or an assignment question? Is that if f satisfies this relationship, prove it's uniformly continuous? I feel like I might have
optional question.
Oh, it was an optional question. Okay, so you can go back, you can find one of your assignments. This is a statement of this. Again, it's a one-line proof, right? Let epsilon greater than 0 be given, delta is epsilon over m, boom, done. Okay, but we've actually proven not only is it continuous, it's uniformly continuous. Differentiability is surprisingly not that hard. So again, we're going to prove that it is differentiable and that it is an antiderivative simultaneously. Right? We're going to do both of them. So we're proving uniform continuity, therefore it's continuous. So now let's show differentiability. Okay, now, if I wrote down the limit, then I'm going to write that. Well, let's write it down, right? What am I trying to show? So let's show that the limit as h goes to 0. You know what? Let me say something first. So let's say suppose that little f is continuous at c, right? Because the theorem says we have to take a point where little f is continuous, right? Big F isn't going to be differentiable everywhere. It's going to be differentiable wherever little f is continuous. So let's start by fixing such a point. Let's suppose little f is continuous at c, okay? Now, let's show that the limit as h approaches 0, f of c plus h minus f of c divided by h is f of c. Right, that's what we want to show, right? That would show, one, we're differentiable because the limit exists, and it would also show that the derivative of capital F at c is equal to little f of c, right? Therefore, that it's an antiderivative. So this is what we want to show. Now, very rarely, I think, in this class, have we had to show this using epsilon delta, right? Normally, when we compute derivatives, we've got all of our nice derivative rules, and we can use them. We don't have to epsilon delta it. This one, we sign, yeah, we got to epsilon delta it. What are we going to do? Okay? So, where are we going to use continuity of f? So let's suppose two things. So first, let's suppose that h is greater than 0. Okay, so I'm going to do the limit as h approaches 0 from the right. And it's just so that we don't have to worry about like signs and stuff. But you would break it into two cases. H is, well, let's say greater than or equal to 0. And then h is less than 0, but the h less than 0 proof is exactly the same, right? You'll see that it doesn't make a difference. So suppose h is greater than or equal to 0, and that epsilon greater than 0 is given. Okay? Since f is continuous, there exists delta greater than 0 such that every x minus c less than delta implies f of x minus f of c is less than epsilon over b minus a. Right, it's been a long time since we had to write that down, but that seems right to me. I'm pretty sure it's over b minus a. So maybe leave that one blank for now, and we'll come back to it and fix it if we want. But if I recall correctly, I'm pretty sure it's b minus a. Just to make our numbers work out. Again, you could leave it as epsilon, and then if we get a number in front, who cares? All right, now I claim that this same delta works. It is better. Okay, so let's epsilon delta this bad boy right here. Okay, so suppose that x, am I doing x? No, let's suppose h. H is in 0 delta. So that okay, there's going to be a lot that we have to parse here, right? We already know, I think it's still on the board, we know that f of c plus h minus f of c, okay, let's think about if we plug that in here. F of c plus h minus f of c, that's going to be the integral from a c to c plus h of f, right? So that part there. So let me actually, let's do, so 1 over h, the integral from c to c plus h f. That's this part. Everyone agree? That makes sense? That looks okay? Right, I just kept the 1 over h. And then this part is on that board. And then maybe let me put this in brackets here just so that we can see that the integral sign does not include that f of c right now. Okay? Now, here's a little bit of magic, but it's not too much magic, it's just a little bit of magic. Okay, so I switched notation back to using dx, and I've somehow put the f of c inside. Okay? Well, let's think about it. Let's think about why this is okay. If I were to actually evaluate, so again, we know by linearity of the integral, I can split this up into two integrals, right? I can split this up into the integral over f of x, and then I can split this up into the integral over f of c, right? But f of c is a constant, so let's maybe come over here. So 1 over h times the integral from c to c plus h, f of c. This is a constant, so this integral here is f of c times c plus h minus c, right? It's the width of that rectangle. Right? So I took this f of c, which was not in the integral, and just was allowed to magically put it inside because this 1 over h is going to cancel the h that I get from here, just giving me that f of c. Everyone's good? Make sense? Subnormality this. Right? Maybe it was just epsilon. I don't even think I need to be minus a. Oh, let me put my dx in. That's less than epsilon. Right? Because x here is always between c and c plus h. Right? Which means, and h here is in 0 delta. That means that x is always within a delta from c. You see that? Is everyone okay? So, I'm going to get less than 1 over h, integral c plus h, epsilon. Again, epsilon's a constant. C plus h. Again, yeah, it is actually just epsilon. I don't even need to be minus a. Which that's cool, right? They use the exact same epsilon. And that's epsilon. So we're done. Right? Now, strictly speaking, that was the limit as we approach 0 from the right. But okay, what would we do if we switched and we had h was less than 0? We just have to be a little bit more careful about like c and c plus a. It doesn't really make that big of a difference. It's just, you have to be a little bit more careful. But it doesn't. It really doesn't make a difference to the proof at all. Okay? Everyone's good? So I think that's cool, right? Like, it literally is just, it magically works. Sort of the only trick is right here. This is sort of the tricky part. But like, again, you would have guessed that you would need to do that somehow, because the only thing I have is continuity, right? I have some sort of statement about f of x minus f of c. Well, how am I going to get f of x and f of c to show up together? I've got to get them both inside that integral, right? So I think, even though that's the tricky part, you probably, if you thought about it long enough, would have come to that conclusion. I got to get that guy in there somehow. And you would have manipulated it until you could have. Okay? So I think we've proven all of FTC1, right? We're continuous, we're differentiable, and we are in fact an antiderivative of little f. That's cool. So that's FTC1. Now FTC2 requires a little bit more trickery, but it's seriously, it's such a slick proof. It's one of my favorite proofs. And it's important to note too that our statement of the FTC here, if you go and you grab like a, because we're doing analysis one, but if you go grab like a calc book, this is not the statement of the FTC that you'll get, okay? So the statement of the FTC that you'll get in like a typical calculus book, like if you pull up Stewart or Thomas or something like that, is a weaker statement than this, because like they'll only state it for continuous functions, and therefore all antiderivatives are differentiable everywhere. So we're dealing in a little bit more generality. But it's okay. The proof is just as easy. Okay, so FTC2. Let's do it. All right. So what did we have? We said that f was a continuous antiderivative, which was differentiable at all but finite limiting points. Right. So let's say let f be the antiderivative. With d. So these are, I'm going to let these be the points where I failed to be differentiable, and I know there's finitely many of them, right? By hypothesis, there's only finitely many of them. The points where f fails to be differentiable. Okay, so what are we trying to show? We're trying to show that the integral of little f is f of capital F of b minus capital F of a, right? So we want to show that for every p in our partitions, we want to show L f p is less than or equal to right? by definition, the integral is the unique number that is always between the lower and upper sums, right? So if I show that for every p, this is true, then that has to be the integral, right? Okay, that's what we want to show. So let's fix an arbitrary p, and then what I'm going to do immediately is I'm going to refine it with this guy. So fix p in the partitioning set, and let's let q be p union d. Okay, so I've added in my differentiability, or my points where I failed to be differentiable. And again, this is going to be okay, because, yeah, when I do a refinement, the lower sums are going to get bigger and the upper sums are going to get smaller. So, this proof is still going to work out as long as I can prove it on this refinement, right? It'll be okay. The inequalities will work out. Now, here's the slick thing. So, what do I want to do here? So note, oh, and let's name this. Let's do this x0, x1. Let's name this new partition, just so that I can refer to it. So note that f is continuous. It's actually continuous everywhere, right? Oops, do I want, yeah, sorry, I want capital F. So capital F is continuous everywhere, right? By FTC 1, capital F is continuous everywhere, but in particular, it's continuous on each subinterval. You can probably guess where I'm starting to go with this. And differentiable right? We know for sure it's differentiable on those intervals. Why? Because we added the end, like the points where I failed to be differentiable, the points D, I put them into my partition, which means the only points where I can fail to be differentiable are at the endpoints of each partitioning set. So I'm differentiable on the interior, right? Right? Because the xi's are the only places where I could potentially fail to be differentiable. So, continuous on the closed interval, differentiable on the open interval. What theorem does this sound like I'm about to use? Oh, it hasn't been that long.
Could you repeat that, please?
Continuous on the closed interval, differentiable on the open interval. What theorem?
MDT?
And the mean value theorem. All right, so we're using MDT. MDT, by the way, is on your next test. I checked. We didn't do the MDT in term test 2, so it's on term test 3. Got a nice MDT question there for you. Anyway, okay, so applying the mean value theorem. So by MDT, there exists some Ci in xi minus 1xi, such that, okay, let's apply this. So we get f xi minus f xi minus 1 is f times ci. Oh, we can do that better. And let me just write delta xi, right? Because we know that's what that is, right? It's going to be xi minus xi minus 1, but that's precisely the length of that partition, right? So I just put that in there now. And because capital F is an antiderivative, that's true, right? That was the magic, because we're done. Now, you're not going to see it yet, but we're done. Okay, so what does this mean? Thus, let me multiply by delta xi. Everyone agrees? Right? So the delta xi, ignore the delta xi. The delta xi is just coming for the ride, right? It's like this thing here is f of c delta xi, right? So every term has the delta xi in it. Don't worry about the delta xi. So the important statement now is that, oh, shoot, I wrote my scoops and amps backwards. What a dumb mistake. Okay. Okay, so this thing here, right, this is f of c delta xi, right? That's what we proved up here. So the statement is the infimum less than f of ci? Well, of course it is, right? Because the infimum is it's the infimum, right? It's smaller than anything. And is f of ci less than or equal to the supremum? Well, of course it is, right? Okay, great. So now, when I sum from I equals 1 to n, here's the lower sum. When I sum from I equals 1, here's the upper sum. And when I sum from I equals 1 to n, that's true, right? What is that? That's a telescoping series, right? So the only thing which survives is the biggest term and the smallest term, i.e. and we're done. That's a wild, I love that proof. It's just so magical, right? That is a slick, slick proof. That one, okay, sure, probably wouldn't have figured that one out on your own, right? That one takes a little bit of time, but FTC 1, you totally could have done. You totally could have done FTC 1 on your own, I think. I could have made it, in fact, 1 year FTC 1 was a test question. Like, we hadn't done FTC yet, the term test was coming up. We did like the FTC the day after, like the lecture after the term test, so they wrote the test in class and I made them prove FTC 1. Maybe I only asked them to prove continuity. I might not have asked them to do the differentiability part. I think I just made them prove continuity. But you can see that continuity proof, proving that the integral there, the accumulator function is uniformly continuous, that's a pretty easy proof, right? It was like 3 lines. It was pretty straightforward. So anyway, that's, I love it. That's so good. FTC for you. Any questions? It took like an hour to prove. But I don't think the proof is like, oh, it's terrible. It's one of my favorite proofs. Just, FTC itself may be kind of boring, but its proof is very, very slick. Very slick proof. Okay? All right, so let's see, how do we use this? Well, there's a couple things we can do. All right, what can we do? What can we do? Let's do some stupid easy stuff, just to begin with. An example. Let's say find the integral from a to b, x squared dx. That's what I made you do on your assignment, right? And now this is true. Right? So let's let capital F of x, an antiderivative for this is x cubed over 3. Again, you can take it in constant if you really wanted to, right? Throw another constant in there, it's not going to make a difference. This is an antiderivative. Of x squared. So the integral, ab x squared dx, is going to be f of b minus f of a. That's going to be b cubed over 3 minus a cubed over 3. And that's what you found in your assignment. Right? Way easier, right, than having to do all these sorts of weird inequalities and basically having to prove this, right? That's what you had to do in your homework thing, is you basically had to do this thing. And you can see the proof is actually very similar, right? The thing that you did in your homework was, again, just set up this, in some sense, this telescoping series. Right? And then the things all canceled out. The only thing that survived was b cubed over a, and or b cubed over 3 and a cubed over 3, right? So effectively, you kind of proved FTC yourself there, though you didn't use the MBT to do it. All right, maybe we'll do something a little bit more interesting. Let's see. All right, another example. So example. Find the integral from 0 to what? Pi by 4? Pi by 4 is an interesting one, I think. Sine theta, cos theta, d theta, right? So this is another one. We were talking about antiderivatives on Tuesday. We talked about how to find an antiderivative for this, and we said there were a bunch of them, right? There were like 3 that we managed to come up with off the top of our head. And again, we can use any of them. So let's set f of theta. What was one? Does anyone remember one? 1/2 sine squared theta? Does that work? Let's check it, right? Because we just differentiate it and see if it works. So if I differentiate this, the 2 comes down to cancel. So I get, oh man, see, I don't differentiate a lot either. So the derivative of sine, I think that works, yes? That's good? Okay? All right, I told you I asked my 257 students to differentiate like x sine x, they couldn't do it? Yeah. That's partially my fault, because how often do we actually differentiate stuff? Okay, so set f of theta to be this. So by the FTC, you don't have to say by FTC, okay? By this point, the only way that we're going to do this is by FTC. So I will be very happy if you just write down the answer, okay? Don't say by FTC. So we're going to get 1/2. I'm going to factor the 1/2 out of everything. You don't have to. That's 0. Okay, sine squared is 0. Sine squared pi over 4 is what? 1/2? Right, sine pi over 4, I think is 1 over root 2.
Yeah.
Yeah? Everyone agrees? I hope so. Anyway, if that's not right, you can figure out what sine pi over 4 is. So sine pi over 4, I'm pretty sure, is 1 over root 2. Sine squared pi over 4 is 1/2. 1/2 times 1/2 is 1/4. That's crazy how easy that is, right? Like, if you had to do this, even if you plotted this thing and I asked you to get an approximation for this, this is a pretty tough computation. And now, just by sort of eyeballing the answer, we managed to compute the integral. That's nuts, right? That's truly insane that we managed to do that. Let's do another example. Now, this is sort of example, it's a little contrived. So far we've been using FTC2 a lot, and most of the time you will use FTC2. But let's try and use FTC1. Now, this is the sort of thing, this doesn't come up too much in real life. It does every now and then, but not too much. So let's say, suppose something like that, okay? Just made up some function. Now, you'd be very tempted to try and integrate this, right? Maybe find an antiderivative for sine t over t, but this is one of those functions that I mentioned the other day that, if I recall correctly, actually does not have an elementary antiderivative, right? So you couldn't just solve this, plug in x squared, plug in x, get an answer, and then differentiate. That is not possible to do, right? So we've got to be a little bit more creative in how we approach this, and this is what I'm saying. This is where we can use FTC1. But that being said, if you could solve this and figure out an antiderivative for that, you could plug in x squared, plug in x, and differentiate. You'd be fine. Okay? But let's suppose we didn't know how to do that. All right, so let's say set, I'm just going to call it g of x, to be the integral from 0 to x sine t over t. Right? So, by FTC1, its derivative is that. Now, that doesn't do us any good right now, because that's not what we were asked to differentiate, right? This has a 0 at the bottom, and again, that 0 doesn't matter. And an x up top, this has got an x and an x squared, right? But that's fine. I know the derivative of g, so let's see now if I can write f in terms of g, right? So f of x is the integral from x to x squared sine t over t dt. That's the integral from x to 0 plus the integral from 0 to x squared. Right? And that's going to be equal to negative, let's let's just put that in there. Negative g of x plus g of x squared. Right? Everyone agrees? Okay? And we can differentiate that now, because we know what the derivative of capital G is, right? So f prime of x, let me switch these around. I'm going to put g of x squared minus g of x. So we're going to get, what, 2xg prime of x squared minus g prime of x. Right? G prime is sine x over x. So we're going to get 2x sine x squared over x squared minus sine x over x. So 2 sine x squared over x minus, oh, we just put that in the numerator like that, and we're done. Right? So we reduced it, we used FTC to reduce it to a problem we didn't know how to solve, and then we wrote our new problem in terms of that reduced problem. Right? So that's an example of that. Now you can actually do this with FTC2 if you want. Okay, if you want to do this with FTC2, even though you can't actually find an antiderivative for sine 2u over t, you can say let, capital G be an antiderivative, right? Which is what I did, right? Like let capital G be just some antiderivative for sine t over t. Therefore, f of x is equal to g of x squared minus g of x, and you can sort of skip the line and go straight to differentiating, right? But nonetheless, sort of a nice example of seeing how FTC1 applies them. Okay? All right, so that's sort of like the basics, and believe it or not, well, I'm not going to ask you to do too many computations in your life. But yeah. Anyway, this is probably a good time to take a break. This is 10:04, let's say 10:05 right now. We'll come back at 15:15. We'll talk a little bit about like the indefinite integrals and some notation, and then I will finally define for you what the logarithm is. Okay? All right, so 10 minutes.